Welcome to C School. In this video, we will learn about the concept of linear magnification by a spherical mirror. Here, we are using a concave mirror. As you can see, this is just an example. However, the meaning of linear magnification remains the same for any types of mirror. As we know, for a concave mirror, it has a pole which is P, a focus point F, and a center of curvature C. Now imagine an object of height h, as you can see here, is placed in front of the mirror. Let us first place this object at the center of curvature C. After reflection, a real and inverted image of the object will be formed at C itself, and the size of the image will be also equal to the size of the object that you can see here. Next, if we move the object towards the mirror, we observe that the image moves away from the mirror, opposite to the movement of the object. As the image moves away from C, its size increases, but it remains real and inverted. On the other hand, if we move the object away from the mirror, the image moves now closer to the mirror. In this case, the image is still real and inverted, but its size becomes smaller when the object is placed beyond the center of curvature and the image moves inside the center of curvature. When the object is placed at focus point F or near to focus point F, then the reflected rays become parallel and the image seems to be formed at infinity. This image is still real but inverted and highly enlarged, as you can see. However, if we place the object between the pole P and the F, that means between P and F point, then the reflected rays is now diverging. It appears to come from a point which is behind the mirror. Therefore, the image formed here is virtual, erect, and enlarged, as you can see, and it appears behind the mirror. You can see for all positions of the object between P and F, the image will always be virtual and enlarged and erect. So, from this experiment, we can see that depending on the positions of the object, the size and nature of the image changes. Sometimes the image is smaller than the object, sometimes it is larger. However, it may be real and inverted, and sometimes it's virtual and erect. The definition of linear magnification, M, is denoted as the ratio of height of the image, which is h dot, to the height of the object, h. So you can see the equation of linear magnification now. Also, if the distance of the image from the pole is denoted as V and the distance of the object is denoted as U, then you can prove, and the magnification can also be expressed as M equals h dot by h equals minus V by U. Here, the negative sign in this formula is very important. When solving numerical problems, always assign positive or negative sign carefully to all quantities such as U, V, F, R, H, h dot, etc. Thank you for watching.